Okay, so in this session, we're going to mostly talk about the relationship between LTL, linear temporal logic, on the one hand, and non-deterministic Buki automata on the other hand. And we've already seen a lot of different relationships between games and our LTL logic and also the automata that we had. For example, in the previous session, we saw basically how you can write Buki properties, Buki objectives, and also parity objectives in terms of LTL formulas. And we already know that we can do this using automata as well. So in this session, I'm going to mostly talk about how you can translate from LTL formulas to non-deterministic Buki automata. Okay. So before I do that, I need to actually define a new type of automaton again. And this is actually something that answers part of the homework, almost answers all of the exercise 2 in homework, but I have to go through it because we need it in the rest of this session. So I want to define something called a generalized non-deterministic Buki automaton, or GNBW. And well, if you remember, we said that basically a non-deterministic automaton on infinite boards consists of several different parts. So there should be a finite alphabet of letters. It's really impossible to teach with this mask. I was overheating. So there should be a finite alphabet of letters and also a finite set of states. And we had a set of initial states. Remember that because it's non-deterministic, we don't have just one initial state, we have a set of initial states. And we also had a transition function, and this transition function was also non-deterministic, meaning that given every state and letter of alphabet, it gave us a set of states that could be the successors of the current state. And then we, of course, needed an acceptance condition. Now, the acceptance condition is really what defines the different types of automata. And the type that we have worked with the most until this point in the course is the Buki automaton. And we said that the acceptance condition in a Buki automaton is basically a target set T, which is a subset of our states. And then a run of the automaton is accepting if it visits this target set T infinitely many times. So if the set of states that are visited infinitely often in this run row intersects with our targets, then the run is accepted. Now, as the name suggests, in a generalized Buki automaton, what we do is that instead of just having one set, we have k different sets, T1 to Tk. And these are also all subsets of our state set Q. And then a run is accepting if and only if it visits each one of these TIs infinitely many times. So the run row is accepting if the set of vertices that are seen infinitely often in row intersects with T1, but also intersects with T2, T3, so on until Tk. And one thing that we are really not interested in is the cases where the run of the automaton is finite. So if you get to a state and read some letter and there are no transitions with that letter out of that state, we don't really like these kinds of runs. So without lots of generality, we are always going to assume that one of these states, one of these accepting sets, for example, T1, is the whole set of states Q. So what this assumption does is that it basically says, if your path is finite, if your run in the automaton is finite, it's a rejecting run, it's not an accepting run. Because every infinite run would visit at least one of the states infinitely often. Okay. So this is our definition of generalized non-deterministic Buki automata. And of course, it's obvious that it's not less expressive than normal Buki automata, right? Because if you have a Buki automaton, it's basically also a generalized Buki automaton with only one set, right? But is it more expressive or are they just the same? And actually, I'm going to show that they have the exact same expressivity. So if I have a GNBW, generalized non-deterministic Boole automaton A, which has all those parts and then K sets, I can actually construct a non-deterministic Boole automaton B such that the languages of these two automata are the same. So I can construct an equivalent non-deterministic Boole automaton. Now, let me first give you the intuition and then I give you the construction, which also solves the homework. So the intuition is that if I have some run row of my automaton, and if this run visits each one of T1 and Tk infinitely many times, then I can actually put an order on these visits. I can say, okay, there is some index I1 where I'm visiting T1. Right, my first target set. Now, I only look at the suffix of the run starting from I1. And then I find another index I2, which is greater than I1, such that this is a place where I'm visiting the second target. So I'm visiting T2. And then I just continue like this. So I get K different indices. And so Ik is greater than Ik minus 1 and so on to I1. And in each of these, I'm visiting one of my target states, right? But then I can just continue with this. Then I can only look at the suffix after Ik and say that, well, I'm visiting my first target set T1 infinitely many times. So in the suffix after Ik, I have to visit T1 again, right? And this gives me another index I prime 1, which is greater than Ik, such that at that index, I'm in T1, and then I can just continue with this over and over again. So basically, the idea is that if you visit each one of these sets infinitely many times, then you can find a bunch of indices such that first you visit T1, then you visit T2, so on, and then you visit Tk, and then you come back and visit T1. So how can we translate this automaton A, which was a generalized non-deterministic Boole automaton, to just a simple Boole automaton? Well, we just do this. We take K copies of our original automaton. And the idea is that you start in the first copy. And you just run the first copy until you get to a target in the first set, in the first target set. And when you get to a target in the first target set, you switch to the second copy. And then you just run normally until you get to a target in the second target set, and then you go to the third copy. And this happens until you get to the case copy. And at that point, if you get to a target in the case target set, you just go back to the first copy. Okay? So basically what I'm doing is that I'm constructing this automaton B, and the alphabet is the same as what it was before, but instead of just the set Q of the states of the original automaton, now I have K copies. And I said that I start in the first copy, so this is the set of starting states. And what are my target states? My target states are basically T1 in the first copy, T2 in the second copy, up until Tk in the case copy. And this definition of transitions, which I'm showing with delta prime, are basically just what I told you, that we run A1 until we get to target 1, and then we switch to the next copy. So if I'm at vertex Q in copy I, and I read the letter sigma, then I just do what the original automaton did with Q, and I stay in the same copy, provided that I'm not at a target set, at a target vertex. But if I'm at a target vertex, then I just go to the next copy. And if I'm already in the last copy in AK and I'm at the target vertex, then I just go back to the first copy. Okay. So it's very easy to prove that these two automata have the same language. Basically, let's do that. So if I have a string that is, if I have an infinite string or an infinite word that is accepted by this automaton B, then what does it mean? It means that it first visited something in T1 so that it could go to T2, visited something there so that it could go on, right? And so it visited at least one vertex in the target sets infinitely many times. So let's say that that vertex that was visited infinitely many times was a vertex in T2. So the first time that we visited that vertex, we were then pushed into the third copy. And then we would never come back to the second copy until we see vertices of each one of the other target sets. Right? So this shows that because I saw this vertex here infinitely many times, I visited each one of the target sets infinitely many times. And you can also do the other side as well. That's also easy. Okay.
I have a question.
Sure.
Is the order of visiting important here in generalized non-deterministic Boole automaton?
No, the order doesn't matter because basically a run is accepting if it visits every one of these target sets infinitely many times, right? So the order doesn't matter.
Okay, so then in the non-deterministic Boole automaton, we should have every possible copy of the cases that all of these sets are being visited.
No, that's
right.
so.
Or no?
No matter what the order is, you can always find these indices that I talked about. So it doesn't matter what the order of your target sets was. You can just, because you know that you have visited T1 infinitely often, you know that there is some index I1 where you visit T1.
Okay, okay, I got the point.
Right? I'm not really relying on order here.
Okay, I got it. Thank you.
Okay. So basically what this tells us is that from now on, we can just work with generalized non-deterministic Boole automata. And whenever we have a GMBW, we can just apply this construction and turn it into an NBW. Okay? And this construction, of course, runs in polynomial time because I'm just taking k copies. Okay, so let's get into the main topic of this session, which is the equivalence between LTL formulas on the one hand and non-deterministic Boole automata on the other hand. So remember that when we were talking about LTL formulas, we had a set P of atomic propositions, and then our alphabet was the set of subsets of P. So every letter in our alphabet is a set of atomic propositions. Okay. So before moving on, I should just say that every example that I use here is taken from a course by Joost Pieter Katoen. And his course is also really great. Just you can watch it on YouTube, and he covers many of the same things that we cover here. Okay, so let's start by saying that an automaton is equivalent to an LTL formula if the language of the automaton is equal to the semantics of the LTL formula. And in the previous session, we basically said that the semantics of an LTL formula is the set of all infinite paths that satisfy that formula. So let's do an exercise here and let's write LTL formulas for this automaton here. So consider this automaton as a non-deterministic Boole automaton. And because my alphabet is 2 to the power of P, so instead of just writing letters of alphabet, I can actually write propositional formulas on my edges, right? So basically this means that from this vertex, we always transition to this vertex because it's true. but from this vertex, we transition to this vertex only if the letter that we read does not have P in it. So P is a propositional atom. Okay. So can you give me an LTL formula that is equivalent to this non-deterministic Buffy automaton? So what strings are accepted by this automaton? So eventually P is not, well, it's not exactly eventually because you have to get here with one step, right? You start here and no matter what happens in the next step, you're here. So you have an infinite string and the first letter is basically ignored because no matter what the first letter is, it satisfies true. And you go here, but then the second letter should satisfy not P. No, it's not eventually not P. It's actually next not P, right? Because, well, the first letter is ignored, and then in the second letter, you should have not P. Otherwise, you can't go there. So if you had some edge here, if you had a self loop here, then it would become eventually not P. But because we don't have that self loop, the only way is to go here. And basically this automaton only accepts strings in which in the second position, P is not satisfied, right? So it's next, not P. Okay. Now let's do it for this automaton. And this is actually the union of two different automatons. So these are both starting vertices. These are both my initial vertices. So what is the formula that is equivalent to this automaton? Yes, the answers in chat are correct. So it's A or B. Because basically, if you look at the top component, it only accepts strings that start with A. And if you look at the bottom component, it only accepts strings that start with B. And it only cares about the first letter in the string. So yeah, this is A or B. And just to be more clear here, so if I have something like A, B, A, so on, this is accepted by this automaton. Because when I'm writing A here, it means that A is part of my first letter. And my first letter is a set of atomic propositions, in this case, A and B. So it satisfies this one. Okay. So basically what I'm saying is that this does not mean that we transition only with A. It means that we transition with any set that contains A. Okay. So what is the language of this third automaton? This B union A. Okay, so well, we can't really use union in our LTL formulas. We can only use until, right? So one answer is B until A. The other answer is always B. Okay, it's actually always B, right? Because we start here, and as long as B is satisfied, we remain here. And when can we go to the other side? Only when B is not satisfied, so it's always B. So again, if I have an input like this, A, B, B, A, B, B, so on. So when I start here, when I read the first letter is AB. So I can either go here or remain here. And it's better to remain here. The next letter is B, I remain here. Then the next letter is AB, and I can go either to the right or remain here, and so on. So this string would be accepted if it has infinite, if it keeps B in there forever. Okay, so this is always B. Now let's make things a little bit more interesting. So what is the formula that is equivalent to this non-deterministic Boole automaton? So we start here, and if in the current point in time A is satisfied, we go here, and then we remain here until A is satisfied. But as soon as A is not satisfied, we go back left, and we remain in the left state for as long as A is not satisfied. Okay, so one answer in chat is always eventually A. That's absolutely correct. So it's always eventually A. So anytime we read an A, we go to the right state, and anytime we read not A, we go to the left state. So, and the right state is accepting, so it accepts if and only if we see infinitely many A's, right? And infinitely many A's in the last session, we saw that is equivalent to always eventually A. Okay, what about this one? So what happens with this automaton? So we start here, and as long as A does not hold or B holds, we remain here. But as soon as we get to a state where A holds and B doesn't hold, we go to the other side and remain there for as long as B does not hold. But then as soon as we see B, we come back. And we want to say that we visit this vertex infinitely often. Right? So what are the cases when I can visit this vertex infinitely often? Well, one case is if I never go to the other side, if I just stay here, right? So if I never get to a case and to a letter that satisfies A and not B. But the other case is that I see that letter, I see A and not B, and I go there, but then I have to see a B in the future to come back, right? So basically what this automaton is saying is that every time you see A and you're not seeing B right at the same time, you have to see B sometime in the future so that you come back, okay? So this is basically always A implies eventually B. Okay, so we always have this, this fact that if we read an A, then we will eventually read a B. Why? Because either we read an A and at the same time we have a B2, in which case we remain here, or we read an A and we don't have a B, in which case we go to the right side and then we have to read another B in the future to come back. So we always have A implies eventually B. Okay, and what about this last one? So I start here, I basically ignore a finite prefix. This is true, so I can always take this edge. I ignore some prefix until I get to a state where I have not A, and then I go here. And as long as I have not A, I wait here, and then until always not. So until actually needs two different parameters, right? So we can't say just until always not A. We have to say what until. Okay. Yes, eventually always not A. Yes, that's correct. So basically, the eventually part comes from ignoring a finite prefix here. And then at some point we read not A, And then when we are at a state where A does not hold, we have to make sure that in the future we never see A, otherwise it would reject. So it's eventually always not A. Okay, so what this shows is that we can basically, in many cases, translate automata to LTL formulas and LTL formulas to equivalent non-deterministic Boole automata. So here's a simple question. Can we use deterministic Boole automaton instead of non-deterministic? So if I have, let's say, any LTL formula, if I give you an LTL formula, can you give me an equivalent deterministic Boole automaton? Okay, so here's the thing. Just take this formula. We know that it has an equivalent non-deterministic Boole automaton. Does it have an equivalent deterministic Boole automaton? So what does this formula say? Eventually, always not A. It just says that we have finitely many A's, right? Because eventually we get to a point from which we will never see A anymore. So we have finitely many A's. And for this, we saw that we have a non-deterministic Boole automaton, but several sessions back, we proved that there is no deterministic Boole automaton for this language. So we can't use deterministic. We have to use non-deterministic. So, but the problem that I really want to focus on in this session is that I am given some LTL formula, and I want to actually construct a non-deterministic Boole automaton that is equivalent to that formula. Okay, I can't do it with deterministic. Okay, so let's try to do the simplest thing. Let's try to just do structural induction. So let me just go through the notation. So I have an LTL formula phi. And the question is whether the semantics of phi, which is the set of infinite words that satisfy phi, forms an omega regular language. Or equivalently, is there some non-deterministic Boole automaton, let's call it automaton of phi, such that the language of that automaton is the same as the set of strings that satisfy phi. And let's first try to do the simplest thing that comes to mind. Let's actually try to make these automata. Let's try to construct them. And let's do this in an inductive way. So for example, when I have phi1 or phi2, I assume that I have automata for each one of these, and then I use those to create an automaton for phi. Okay, the simplest case, if phi is true, then every string satisfies phi. So all I need is a non-deterministic Boole automaton that accepts everything, right? And I can have it like this. Like, it doesn't matter what you give it, it just remains in the one accepting state forever. Okay, what happens if my formula is just P, like an atomic proposition? So if my formula is an atomic proposition, we said that this means that this atomic proposition should hold at the beginning of the string, so at time 0, right?
Then it will be 2 states.
Yes, exactly. So you just start here, and the only condition is that in your first letter, you have to have P. And as soon as you had that, you don't care about the rest of the string. But if you don't have P in your first letter, then there's no transition, so it just rejects. Okay. Now, how can we do OR? So what happens if phi is phi1 or phi2? Well, then in the semantics part, we saw that the semantics of phi would just be the union of the semantics of phi1 and phi2. And by induction, we know that we have automata for each one of these. So we can just take the union of those two automata. So this is just union of the non-deterministic Bookie automatons for phi1 and phi2. And the same, something very similar actually happens with negation. So if my formula phi is the negation of some other formula phi prime, we saw several sessions back how we can actually compute the complement of a non-deterministic Bookie automaton. This was Bookie's construction. So you can just take the non-deterministic Bookie automaton that you have for phi prime and just complement it. Okay, finally, well, not exactly finally, next case is what happens if phi starts with the next operator. So phi is next phi prime. So this means that ignoring the first letter and only looking at the suffix that starts at index 1, I want to have phi prime. So the construction is actually quite easy in this case as well. I just take the automaton that I had for phi prime. I have such an automaton by induction hypothesis. So I just add one dummy state and I start here and I don't care what I read. I just go to the initial states of this automaton. So this just ignores the first letter and then we should have phi prime in the rest. Okay. But the case that is actually tricky and we cannot do this easily is until. So let's say that I have two different automata, one for phi1 and one for phi2. What happens when I want to do phi1 until phi2? Well, the thing that happens is that we actually saw this equivalence in the previous session. So phi1 until phi2 holds if either phi2 holds right now or phi1 holds right now, and then in the next step, phi1 until phi2 holds, right? But how can we really translate this to an automaton? Well, we can have some starting state, and from that starting state, we want to accept all the strings that satisfy phi1 until phi2. But then we have to somehow make a choice at which point we want to see phi2. So this is where we really need non-determinism. But at the same time, even if you know exactly at what index you want to do this, phi1 itself can have until inside it, right? So you have this problem that even if you say, okay, up until index 10, I want to have phi1, and from index 11, I want to have phi2, right? Having phi1 at index 5 also talks about everything that comes in the suffix starting at index 5. So everything that comes in the future. So it's not so easy to make an automaton for this case. And that's actually the reason behind this whole session. And this whole session, we're going to talk about how we can do this. Okay, so basically the simple approach using structural induction fails because we can't really create this one. Okay, so let's take a different approach. Let's say that I have an LTL formula phi, and instead of a non-deterministic Bookie automaton, let's say that I want a generalized non-deterministic Bookie automaton. That is equivalent to this LTL formula. Now, why can I do this? Because, well, at the very beginning of the session, I showed you how you can translate from generalized Bookie to just Bookie. So this is fine. Now, what I want to do is that I want to basically keep track of which subformulas are satisfied at every suffix of my input. So let's say I have some input, which is an infinite word, and every letter of this word is a set of atomic propositions. And what I want to do is that I want to say, okay, if I look at the whole string, then the formula phi holds. But if I look only at the suffix starting at index 1, then some other formula holds. If I look only at the suffix starting from index 2, then some other formula holds, and so on. I basically want to keep track of the formulas that hold at every suffix. So ignoring any finite prefix and just taking the rest of the input, what formulas hold. And I basically want to have different states in my automaton. So for every set of subformulas, for every set of formulas, let's say, I want to have a state in my automaton that only accepts the strings that satisfy those formulas. Okay, but let's not get ahead of ourselves, and let's just define what kind of formulas we're really interested in. Okay, so this was the LTL syntax. So we have true, we have atomic propositions, we have and, negation, next, and until. And we saw that everything else can be defined as syntactic sugar over this. So we just focus on formulas of this form. So let's first look at the subformulas of a given formula. So if I have a formula phi, I define a set SF of phi, which is the set of subformulas of phi. And the definition is inductive and recursive. So basically, true has only one subformula, which is just true. And the same goes for atomic propositions. If you have phi1 and phi2, then its subformulas are itself, and whatever is a subformula of phi1 and whatever is a subformula of phi2. And for negation, its subformulas is itself and also subformulas of phi. And we can write the exact same things for next and until. Okay, so basically a subformula is just part of the formula, that's all. And we also define something which is called closure, and the closure of a formula phi is basically the set of its subformulas and also the negations of the subformulas. So if psi is a subformula of phi, then both psi and negation of psi are in the closure of phi. Okay, so let's do an exercise. Let's say that my formula phi is this. So my formula is A and next A until A and not next A. Okay. What are the subformulas of this formula phi? So of course we have A itself, right? And we have next A here. And then we have A and next A. Here we have A, which we had before as well, but we also have negation of next A. And then at this point we have A and not next A. And finally we have phi itself, right? So these are the subformulas. But what is the closure of phi? It's basically the set of subformulas and also their negations. So you have A, and you will also have, you can type this, I have to copy it. You have also negation of A. You have next A, so you should have its negation. Well, you already have it here. You have A and next A, so you should have its negation. So just take the negation of this formula. You have not next A, so you should also have its negation. Well, we already have it here. You have this formula, so you should have its negation as well. And you have the original formula phi. You should have negation of phi as well. So this is the closure of this formula phi. Okay. So what do I want to do now? I want to have an automaton such that every state of my automaton is a subset of these formulas in the closure. So to every state of the automaton, I assign several different formulas, a set of formulas, maybe more than one. And the idea is that if I'm at some vertex Q of the automaton, I want to accept all strings starting from that vertex. I want to accept all strings that satisfy all of the formulas that are assigned to this vertex of the automaton. So each vertex of my automaton corresponds to a subset of these formulas. Okay? But does this really make sense? So how many formulas do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 formulas in the closure. And if I want to create a state for every subset of this, then I will have 2 to the power of 10, which is 1024 states in my automaton. But actually, some of these states are ridiculous and we don't need them. So, okay. Okay. Now, before talking about that, before talking about how to simplify, let me talk a little bit about the intuition and then I'll come back. Okay, so we have an automaton and every state of our automaton corresponds to a subset of these formulas which are in the closure of phi. Okay. Now, what do I want to do? What I want to do is this. So let's say that I have some input word or input trace W, which is W0, W1, and so on. And this is in sigma omega, so it's infinite. And because our sigma was 2 to the power of p, so each letter is a subset of atomic propositions. Now, let's say that I get a run of my automaton over this trace W. And let's call that run rho. And let's say that the states that I see in this run are Q0, Q1, and so on. Now, if W satisfies my initial formula phi, then I want to make sure that there is at least one such run rho that corresponds to W, such that basically every suffix of W, if I just look at W from index I onwards, satisfies all the formulas in the I state in my run in Qi. Okay, so let me give you an example of this. So let's say that my formula phi is this, A until not A and B. And just to save space, let's say that I call this part of the formula psi. So psi is not A and B. And let's say that I have a run that actually satisfies this formula. So the run that I have here is A, B, B, and then just the empty set. So why does it satisfy this formula? Well, because we have A here until at this point, we don't have A and have B, right? So this is the point where the until is being satisfied. Now, what do I want to do? I want to basically have a run. And so at the first letter, I want to be at a state where basically I have these formulas. So I want the first state of my run to be the set of all formulas that are satisfied by the whole word, right? So this whole word, if you look at it, it satisfies phi, it satisfies A because it starts with A. It does not satisfy B because it doesn't have B in its first letter, so it satisfies not B. And it doesn't satisfy this subformula either. It doesn't satisfy not A and B, right? So I want to have a state in my automaton, which should also be an initial state because I'm starting here, that is characterized by these formula, by these different formulas. Now, for the next letter, I also want to have a state that consists of all the formulas that are satisfied by this suffix, by the suffix that starts at index 2. And again, we can just check. So if we start at index 2, we will satisfy phi because, well, at this point we see B and Before that, we had A. We satisfy A, we don't satisfy B, and you can also check that we don't satisfy psi. Okay. Now we go one step further. So if I only look at the suffix that starts from here, it actually now satisfies both A and B, because this is the first letter of the suffix and it has both A and B in it, right? You can also check that it satisfies phi, but it does not satisfy psi. And that's because, well, in order to satisfy psi, it has to satisfy not A, and it doesn't. Okay. And then we do the same thing here. So, and then just continue. So what this gives us is basically a sequence of states. And as I said before, each state is a set of formulas. And the intuition is that these are the formulas that are satisfied in the suffix starting from that point. Now, this is what we ideally want, right? So what I want is that I want to have some automaton in which we have this kind of a run. And I also want this run to be accepting. But I have to actually construct that automaton now. Okay. So let's go on and talk about this. So first of all, if you look at the states that appear here, the set of formulas that appear in these runs, not every set of formulas is really suitable or can appear. So some sets of formulas are actually contradictory. Some sets of formulas can never be satisfied by any suffix anyway, right? So if my formula is just false, it's not satisfied by anything. If I have two different formulas, P and not P, well, of course, I don't have any suffix of any word that satisfies both of these, right? Or even if I have something like this, if I have psi1 until psi2, but I also have not psi1 and not psi2, what does this mean? This means that at the current point in time, my suffix from here onwards satisfies psi1 until psi2, but it doesn't satisfy any one of them. That makes no sense. There's no such suffix, right? Because it should either satisfy psi2 right now, or if it doesn't satisfy psi2, then it should satisfy psi1 until at some point we get to psi2. So there are some subsets that are contradictory, and we can just get rid of those. We don't need any states for those, because there is nothing that we can accept using those. Okay. And then on the other hand, there are some subsets that just have two-letter information. So if our set of atomic propositions are A and B, then I don't really want to have a state in my automaton for just A. Why? Because this is not telling me anything about B. I'd rather just chop this down and have two different states, one for AB and one for A not B. Right? So we have to actually be a little bit picky about the kind of subsets that we use as our states in the automaton. And this is why we define something called elementary subsets. And elementary subsets are basically the subsets that don't have these two problems. So they always have enough information for us, and also they're not contradictory. Okay. So what is formally an elementary subset? An elementary subset is a subset of the formulas in the closure. So a subset of these formulas that we had here, such that it satisfies the following. So the first thing that it should satisfy is that it should be consistent, so it shouldn't be contradictory. And it should be the maximal, it should be a maximal consistent subset according to propositional logic. So what do I mean by this? Exactly what I mean is that if there is some formula psi, let's say that I have a formula psi in the set of formulas, and I also have this psi1 and psi2. Then I want to satisfy these conditions. What do I want? Well, in my elementary subset, I want to have psi if and only if I don't have its negation, right? This is easy because if I have both of them, then I'm not consistent, I'm contradicting myself. And if I have only one of them, I don't have enough information, right? So I want to have exactly one of these. And I want to have psi1 and psi2 if and only if I have both of them. So this is again about being consistent. So if I satisfy psi1 and I satisfy psi2, I satisfy both of them. And also if true is in the set of formulas that I'm talking about in my closure, then I want true to also be in this elementary subset. Okay. So these were the conditions that we had to satisfy with respect to propositional logic. But there are also some conditions that we need to satisfy with respect to until, right? Because, for example, we didn't want this kind of set. We didn't want to have this kind of contradiction. So we should basically also respect the semantics of until. So if in my set of formulas, I have psi1 until psi2, and I don't have psi2 itself, then I should definitely have psi1. Why? Because if I want to satisfy psi1 until psi2, and I know that at this point I don't satisfy psi2, then of course I should satisfy psi1 and keep satisfying psi1 until I get to psi2. And also, if I have psi2, then I know that I definitely have psi1 until psi2 as well, right? Because this one implies this one. Okay. So what did we do? We started with these different formulas that were basically obtained from the sub-formulas of the original formula and also their negations. And we said that we just take subsets of these and use these subsets as the states for our automaton. So if I have P formulas here, my automaton can have up to 2 to the power of P different states. But then I said that some of these states are just contradictory or stupid or don't have enough information, and I get rid of them. I defined what I exactly mean by that, and I said that I only keep the elementary subsets, which are the subsets that satisfy these good conditions. Okay, so we are doing the definition of our automaton, and we did the first step. Now we know at least what our set Q, what the states of our automaton are. And the states of our automaton are just these elementary subsets, okay? So let's do an example of this. Let's actually try to build the elementary subsets for our favorite formula phi, this one. So I'm just writing the sub-formulas, right? And I'm not writing their negations because, well, if I, by this rule, if I put a formula in my subset, I will not put its negation in my subset, right? So let's just see what different elementary subsets we have. So let's say that I'm creating a subset that does not have the formula A. And let's say that it does not have the formula next A either. Okay. Now, because I don't have A or next A in my subset, I cannot have A and next A, right? This is based on this rule. So you have the and if and only if you have both parts of it. So I cannot have this one. And so what about this one? So again, because I don't have A, I cannot have A and anything else. So I don't have this one either. Would I then have phi? Well, note that phi is basically this one until this one. So, and I don't have either one of these, so I cannot have phi either. Okay. So this is my first elementary subset. What does this mean? It means that my first elementary subset consists of which formulas? Well, it doesn't have A in it, so it should have negation of A in it. It doesn't have next A in it, so it should have negation of next A, and so on. So my first elementary set consists of the negations of all these formulas here. Okay. Now, okay, sorry, no, I made a mistake at this point. Really sorry. So let's do this again. So we decided that we don't want A and we don't want next A, and we got this by the rules. So what is the rule for until? The rule for until is that if we have psi1 until psi2, and we don't have psi2, then we must have psi1. So if I put a 1 here, this is psi1 until psi2. Phi is psi1 until psi2. If I put a 1 here, because I don't have psi2, I should have psi1, okay? And I don't have that, so I cannot put a 1 here. That was actually correct. So this is it. Okay, so this is my first subset, my first elementary subset. And in my automaton, I create some state called Q0, which corresponds to this elementary subset here. Okay, what is my second elementary subset? So let's say that this time I don't want to have A, but I want to have next A. Okay. Now again, according to these rules of propositional logic, because I don't have A, I cannot have A and anything else. So this becomes 0. This also becomes 0 because I don't have A. And this is again similar to the previous case. So this is also 0. So my second elementary subset consists of the following formulas: not A, next A, not A and next A, not A and not next A, and also not phi. This is my second elementary subset. And I create a state in my automaton. I call that state Q1. And that state corresponds to these formulas. So when I say that state corresponds to these formulas, I mean that if you start the automaton from that state, it should only accept strings that satisfy these formulas. Okay. Now, what else can we have? So we can have we can start with 1, 0. So let's say that I have A, but I don't have next A. So because I don't have next A, I cannot have A and next A. So this one is also 0. But I have A and I don't have next A. So I have not next A. So I have their AND. So I have this one. Now, let's look at the rule for until again. The rule for until was that if I put it in, if I put psi1 until psi2 in, and psi2 is not in, then I must definitely have psi1 in, right? Okay, so this is my psi1, this is my psi2. In this case, psi2 is in. So this rule does not apply. The first rule does not apply. But the second rule applies. The second rule says that if psi2, the thing that comes on the right-hand side of the until, is in our set, then we should also have the until itself. So this would become 1. So this is our next elementary subset. It consists of these formulas: A, not next A, not A and next A and not next A, and also phi. Okay. And again, I put it in the automaton and I call this state Q2. Okay, let's just continue with this and create our next states. So let's say that I have 1 here and 1 here. So because both of these are 1, then their AND is also 1, right? And this one, well, the second part does not hold. I'm going very fast, so this one would be 0. Now, what happens here? So Let's look at the rules of until. So it says if you put this psi1 or psi1 until psi2, and you don't put psi2, then you should put psi1. Okay. So here, basically what it says is that if I put a 1 here, because I have a 0 for psi2, then I should have a 1 for psi1. And that's fine. So this is another one of my subsets. But I can also put 0 in the last position there. So let's just take the same thing as before, and let's see what happens if we put a 0 here. So this rule only talks about when you put a 1 for psi1 until psi2. But there is also another rule that says that if psi2 is in, then you should definitely put this one in as well. But here psi2 is not in, so I can just decide not to put phi in as well. So as you see, the rules actually give us some choices sometimes. So any subset that satisfies these rules is fine. And these two subsets both satisfy. Okay. So actually, instead of 1024 states, which was the worst case, as you see, we have only 5 elementary states. So now what I know is that I will have an automaton, a generalized non-deterministic Boole automaton, in which I have these 5 states, right? But let's see. So I started with the formula. I defined my set of states. What else should I define? So I should define my alphabet. Well, the alphabet is always the same. I defined my set of states. Now I should also define my set of initial states. So what states in my automaton are initial states? Again, let's go back to the intuition. The intuition was that if you start at a state Q0 and you have, let's say, 5 formulas at this state, then a string is accepted if and only if it satisfies all 5 of these formulas, right? What do we want? We want to accept a string if and only if it satisfies formula phi, and we don't care about the other formulas at all. So which states of the automaton should be initial states? Well, any state that includes the formula phi. Because I don't care what else I satisfy. As long as I satisfy phi, I'm happy. Okay. So my initial states are the set of all states that include phi. Okay. Going back here. So I had 5 states, Q0 to Q4. Which ones include phi? Q2 and Q3. So Q2 and Q3 are my initial states in my automaton. Okay, what's next? We have to also define transitions. We have to define the edges in the automaton. We have to define the function delta. Okay, let's try to do that. Okay, let's say that I want to define delta of Q and Wi. What this means is that I'm standing at state Q of my automaton, and I have read a letter Wi. Let's just check the types of the different objects that we're talking about here. So what is Q? Q is a state of my automaton. So it's an elementary set. So it's basically a set of formulas. What is Wi? Wi is a letter. But we said that every letter is a subset of propositional variables, of atomic propositions, right? So we had this set P of atomic propositions, and we said every letter of our alphabet is a subset of it. Okay? And also our automaton is non-deterministic. So when I'm talking about the transition from Q using Wi, I'm not going to go to only one successor state. It is possible that I'm going to several successor states. Okay. Let me give you a rule first, and this is the first rule. So my first rule is that I go into the set of formulas in Q, and I look for formulas that are just atomic propositions. And I say that the atomic propositions in Q should be exactly equal to Wi, the letter that I have just read. And if they were not equal, I just reject. So I don't have any successor state. Why? Well, because Q is a set of formulas, and it's also a state in my automaton. And starting from this state, I only want to accept those strings that satisfy all of these formulas. So if one of my formulas is just an atomic proposition, what it means is that at the first letter of that string, this atomic proposition should hold, right? So the first letter of my string should exactly be the set of atomic propositions that are in the formulas of the current state. And if it's not equal, then I just reject. Does that make sense to everyone? Any questions? Okay. So that's the first rule. Now, if you go back and think about LTL, so we had these atomic propositions that we were handling, but we also had until and next. So we need another rule to take care of until and next. So let's say that actually Wi was Q intersection P. So Wi was exactly equal to the set of atomic propositions that appeared as formulas in my state Q. Okay, so this means that starting from Q, I can at least take one step. But what happens when I take one step? So let's say that I started at state Q, I read the letter Wi, and I took one step and got to the state Q prime. What conditions should be satisfied between Q, Wi, and Q prime? Well, let's first look at the case for next. If in Q, if in the state that I started with, I had a formula that was of this form, next psi. What does this say? This says that in the next state, psi should hold. So if Q prime is a next state, Q prime is again a set of formulas, and it should include psi, because I had next psi at the current time. So in the next time, I have to have psi itself. So this is the rule that we have for next. And we actually define our rules as if and only if. So next psi is in the current state, if and only if psi is in the next state. What happens for until? Well, for until, we can again just do this expansion rule that we had on until. So if at the current point in time in Q, I have a formula psi1 until psi2 that I have to satisfy. Well, what does this mean? This means that either psi2 should be satisfied in Q, which means that psi2 should be a formula in Q, or psi1 should be in Q, and then psi1 until psi2 should be satisfied in the next step, and the next step is now Q prime. Right? So I can just write this. So I can write that we have psi1 until psi2 in our current state Q. Again, remember that our states are sets of formulas. So I have this formula in my set right now, in my set Q. If and only if this holds, either I have the second part in my current set, or I have the first part in my current set and have the same formula again in the next set, which is the next state in the automaton, which is Q prime. Okay, so this defines the transitions. Let's actually do this. So we talked about which states are initial states. Q2 and Q3 were initial states. Q2 and Q3. But let's now see what happens if I start at state Q3 and the letter that I'm reading right now is A. Okay, so I'm starting at Q3 and the letter I'm reading is A. So first of all, this is okay because I have the formula A in Q3, but I also have next A in Q3. So in the next step, in any of the successors, I should have what? I should have A. So anything that does not have A in it cannot be a successor. So Q0 and Q1 are out. We can potentially only have Q2 and Q4. Okay. And what else? I also have phi itself, which is this until this. So when does this hold? Either the left-hand side should already be here, which either the right-hand side should already be here, which it isn't, or the left-hand side should be here. And in the next stage, I should have the same thing. I should have phi again. So I can only take the ones from between Q2 and Q4 in which phi is satisfied, and that's just Q2. Right? So if I'm at Q3 and I read A, I can only go to Q2. Let me see if I computed that correctly. Oh, yeah, and I didn't remember. Actually, from Q3, if you read A, you can go to Q3 itself as well. Why? Because, well, you should have next A, so you should have A in the successor, which is okay in Q3. And we also saw that we should have phi in the successor, which is also okay in Q3. So starting from Q3 and reading A, we can go to either Q2 or stay at the same place. Okay. What happens if I'm at Q3 and the letter that I read is the empty set? Well, Q3 contains the formula A. So if the letter is the empty set, I have to reject. I cannot have any successors. So there are no successors here. Okay. Now, we can do the same with the other ones. So what happens if I'm at Q2 and the letter that I read is A? Okay, so I'm at Q2, I read A. I don't have next A, so that's okay. But I have this, I have phi. Because I have phi, either I should have this one here, which I do, or I should have, okay, either I should have this one here, which I do, or I should have the same phi in the next step. So I don't get any constraints out of having phi in Q2. But I don't have next A in Q2, so I have not next A in Q2. And so in the next step, I should have not A. So in the next step, A should be 0, so only Q0 and Q1 can be the successors. So if I start with Q2 and I read A, I can only go to Q0 and Q1. Okay, and then similarly, we can compute for all of the other ones. I'm running out of time, so I'm not going to do that. So this gives us the transitions. So yes. Now, okay, and this is the final part of it. So we created our whole automaton, and the only thing that is remaining is the accepting condition. So how should we define our accepting condition? And this is also not so hard. So first of all, we have an observation. If our original formula phi has no until in it, so let's say that my formula was only created using and, negation, true, propositional atoms, and so on, and it can have next, but it doesn't have until. Then I really don't need any target sets. I can just have the trivial target set, which is that the path should be infinite. Why? Well, because if I don't have any until, the way that I defined my transitions makes sure that I can only transition at every step if I satisfy all the formulas in the current in the current state, right? So for example, if I'm at state, let's say Q2, I cannot move forward without satisfying A, right? Or if I'm in state Q3, where I have next A, I can only move to states where I have A. So I cannot make any moves that do not satisfy next A, right? And you can just check all the cases and see that this works if the formula has no until. But if our formula has until in there, then some things can go wrong. And here's what can go wrong. So let's say that in my automaton, I have a state here which contains the formula psi1 until psi2, and it also contains the formula psi1. So from this state, I can have a transition to another state that contains these same formulas and probably some more. And then I can just continue with this. And then I can go into a cycle. So basically, at every step, I can say, okay, I will satisfy psi1 until psi2 by staying in psi1 currently and hoping to see psi2 sometime in the future. But the problem is that I have a cycle, so I never actually see psi2. Okay? And this means that basically I don't satisfy psi1 until psi2, because in order to satisfy psi1 until psi2 based on the semantics, there should be some point in time where you see psi2. So we have to use the accepting conditions to force us to see psi2 whenever we see psi1 until psi2. And to do this, we basically define one target set. So in our generalized Bookey automaton, we can have, well, at the beginning of the session, we saw that we can have k different target sets, right? And we always have this trivial target set, which is all the states. But we also put one target set for every subformula or every formula in the closure that has this form, that has an until. Okay? And what is the target set that we define? Well, we want to avoid this bad case. So we want to say that we either don't get here, or whenever we get to this until, we will eventually get to the second part, right? And I can do it by defining this. I can do it by saying that I define a target set, which is the set of all states that either do not have this psi1 until psi2 in them, or they have psi2 in them. Okay? So what does this tell me? If I visit this set infinitely many times, it tells me that whenever I visit a state that has psi1 until psi2 in its formulas, I will eventually visit a state that has psi2. Why? Because if I don't visit a state that has psi2, I will just keep on seeing psi1 until psi2. And I will not see psi2, and then I will visit this whole thing finitely many times. Okay? So then we just define our generalized Bookey automaton as having these target sets. We have the trivial target set T1, which is the whole automaton. And then for every formula that has an until, we have this set. So this ensures that this kind of cycle never happens. And with this, you can then easily prove that the automaton accepts exactly the set of infinite paths that satisfy the LTL formula. Okay, so let's just do it here. So in this automaton, for this formula, T1 is every state. This is Q. But the only until that we have is actually this one, right? And we said that the set that we create for this until is the set of all states that either do not contain this until or contain its second part, right? Okay, so let's go back here. So the states that do not contain the until are Q0, Q1, and Q4. and the sets that contain its second part are Q2. So we just put this Q0, Q1, Q2, and Q4. And so everything other than Q3. Q0, Q1, Q2, and Q4. So we now have this automaton, which is a generalized non-deterministic Cookie automaton with two target sets. So it accepts a run if and only if it visits both of these target sets infinitely often. And the language of this automaton is exactly the set of infinite paths or infinite strings or traces that satisfy this formula phi. Okay, so in summary, for every LTL formula phi, there is a generalized non-deterministic Cookie automaton A such that the language of A is equal to the semantics of phi. And also you can easily see that the size of A is exponential in terms of the length of the original formula. Why? Because we created exponentially many subformulas. Okay, sorry, because we created exponentially many subsets of subformulas. So the number of subformulas is actually polynomial, and then the number of subsets of subformulas, which are our states, is exponential. And also at the very beginning of the session, we saw that if we have a generalized Cookie automaton, we can, in polynomial time, translate it to an equivalent normal Cookie automaton, normal non-deterministic Cookie automaton. So what we showed this session was basically that for every LTL formula phi, there is some non-deterministic Cookie automaton B, whose language is exactly the set of traces that satisfy the formula phi. And also the size of the automaton is exponential in the length of the formula. Okay. And sorry for going 5 minutes over time. That's it for this session. And if you have any questions, please ask.